This is Dr. Muhammad, and this is our 8th video. We are going to talk today about the non-homogeneous equation, and we're going to talk about the variation of parameters. This is the case where that we are going to talk about for today. Okay, so again, to highlight the main important parts in this title of our video, today we are going to talk about the non-homogeneous. Okay, before we were talking about the homogeneous equation, but today we are going to talk about the non-homogeneous equation, and we are going to talk about one way for obtaining the general solution using something called variation of parameters. Okay, now let's go and see how we are going to use this. Okay, first of all, before going and indulging into this topic, I want to recall, I want you to recall the solution of the non-homogeneous linear equation that we have already talked about before in the previous lectures or the previous videos. So I want to highlight the main difference, and we want to highlight what is the main, what we can say, distinguishing thing between the homogeneous and non-homogeneous. We mentioned that before. We said that the main difference between the homogeneous and non-homogeneous cases is that for the non-homogeneous equation, sums and constants or constant multiples of solutions need not to be solutions. Okay, that's the main thing here, which is the sums and constant multiples of the solutions need not to be solution. Actually, this is something important, and this is one of the things that is making the homogeneous equation to be easier for solution, that any type or any multiple of solutions, if we just sum them up, then we're going to obtain the general solution. Okay? But here in the non-homogeneous, it's a little bit different. We're going to find, first of all, in the right-hand side, we are not going to find the zero as it is usual in the homogeneous case. We're going to find a function of x. Okay? But the left-hand side, it is really the same as what we accustomed to or used to see when we were solving for the homogeneous equation. And we mentioned that if we are going to assume something called yp, which is the particular solution, okay, let yp any solution of the homogeneous equation, 2.1, I think there is a wrong here something. It should be non-homogeneous, sorry. Here it is non-homogeneous. So if we're going to say that yp, okay, is a solution for the non-homogeneous equation, which is 2.1, as you can see, then let y1 and y2 be linearly independent. This is very important. Linearly independent, let's remove this. Linearly independent solutions of equation 2.2, which is the homogeneous equation. Now we are 2.2, it is the homogeneous equation. Then the expression for the solution of the non-homogeneous equation, which is going to be c1y1 plus c2y2 plus yp, is going to be the general solution of the non-homogeneous equation. And the general solution means that it contains every solution of the non-homogeneous equation. Okay? So this is something that we want to highlight and we want to keep in our mind. What is the major difference between homogeneous and non-homogeneous? And what is the form of the general solution? As you can see here, in order to obtain the general solution of the non-homogeneous equation, we need to get what? Exactly. The two independent solutions first of the homogeneous equation or the associated homogeneous equation. This is a prerequisite in order to obtain the general solution of our non-homogeneous equation. Okay? So now we have, or up till now before this video, we have explained some strategies regarding how to obtain y1 and y2 of the homogeneous equation if you review the previous video. But today we're going to talk about yp, how to obtain yp that is needed to be added to the two solutions of the associated homogeneous equation in order to obtain the general solution of the non-homogeneous equation. Okay, so now to the last time I'm going to say that the general solution of the non-homogeneous equation consists of two parts. One part related to the associated homogeneous equation, which is going to be C1y1 plus C2y2, and the other part is related to the non-homogeneous equation solution. We call it particular, okay? We call it particular solution because it's only some, or for particular, we can say it is a particular, something like unique solution, for example, for this differential or non-homogeneous equation, okay? Okay. Now let's go to find or to recall what we have explained before regarding the strategy for finding all solutions of the non-homogeneous equation. What we are going to do, we have explained that before, but I'm going to recall it because it is important for today. Okay, first of all, we're going to find two linearly independent solutions, y1 and y2. This is from where we can obtain them. Look to the previous video. Of the associated homogeneous equation. What is the meaning of associated homogeneous equation? It is the left-hand side equating with 0, this one. Okay, this is the left-hand side, we equate it with 0. So if there is a function here, we remove it and equate or put it 0, then this is the associated homogeneous equation. Okay, we can perform the first task at least when the coefficients are constant, because already we have explained before regarding constant coefficients and how we can obtain the solutions for the constant coefficients homogeneous differential equation. Okay, so number one, or step one, is already done and we know well how to do it. Let's go to the step number two. Find any particular solution yp of the non-homogeneous equation, Okay, so we are going to talk today about how to get this kind of particular solution, okay, which is for the non-homogeneous equation, and the right hand side here is going to be f of x. Then step number three, the general solution of this non-homogeneous equation is going to be like this: c1y1 plus c2y2 plus yp. This is the general solution. Okay, as we said, these two terms, they are related to the associated homogeneous equation, and the last term, it is going to be something new that we're going to learn for today. Okay, and this C1 and C2 can be any real numbers. They are constants. Okay, they are constants. Remember well, in the constant coefficients, if you remember, we said that we can obtain the general solution of the homogeneous equation, which is C1 y1 plus C2 y2, right? This considered to be general solution for the homogeneous. But every term of them is considered to be a solution for the homogeneous equation, right? We call both of them as the fundamental set of solutions. Okay. Then if there are initial conditions, we can use these to find constants C1 and C2 to solve the initial value problem. Okay, this is for the case of initial value problem. Okay, let's go and jump into the next slide. Now we're going to talk about the variation of parameters. Okay, variation of parameters. What is the main, or what is the final destination after knowing this variation of parameters? We are seeking for what? Exactly, we're seeking of yp, particular solution. We want to find this yp, the particular solution. Okay, this is what we want to get. Okay, so now for the variation of parameters, suppose we know two linearly independent solutions, y1 and y2, of the associated homogeneous equation. One strategy for finding yp is called method of variation of parameters. Okay, now how to obtain this variation of parameters and what are the derivation? You can find this in the textbook. I'm going to focus here on how to use the method itself rather than the derivation of the y particular. Okay, so suppose we are actually found that, or after the derivation, you're going to find that y particular, to some way or another, it is related to the previous solutions of the homogeneous equation. So you can see here, we are putting y1 of x and we put y2 of x. But there is something new that we have added here, which is something called u1 of x, and there is another function called u2 of x. So we know y1, y2 from the solution of the associated homogeneous equation, but we do not know u1 of x and u2 of x. We do not know. We have no idea about this. There is a derivation, as I said in the textbook, on how we can get this u1 and u2, but we are going to end up with what you are going to see in this slide. Okay, we're going to end up after the derivation. If you like, you can look and you can go through the derivation in the textbook, but you're not going to be asked in the exam regarding this derivation. Just it is for your information, and you can understand it for your own. Okay, u1 of x equals to, yes, minus the integration of y2 of x, which is coming from the associated homogeneous equation, the solution, one set of the solution, one solution of the associated homogeneous equation, times f of x. What is f of x? Exactly, it is the right-hand side of the non-homogeneous equation, over w of x. What is w of x? Do you remember it? 2 lectures before, we have explained about it. We called it what? Yes, the Reniskian. Do you remember the Reniskian of the homogeneous solution or set of solutions? We said that the Reniskian for y1 and y2 equals to y1, the determinant of y1 and y1 prime here, y2 prime here, and this is the Reniskian. Okay, after multiplication of the diagonals and subtraction of the diagonals, we can obtain this. This is the Reniskian. So u1 is going to equal to minus the integration of u2x times f of x over the Reniskian of the associated homogeneous equation set of solutions. Similarly, u2 is going to be, take care there is no minus here, okay? It is going to equal to y1, we know it already we have obtained it before, times f of x, already it is given for our non-homogeneous equation, right-hand side, and the Reniskian, already we know it and we have explained it here, right? Okay, once we have u1 and u2, we have a particular solution. What is the particular solution? This is the particular solution here. This is the one. yp equal to u1 y1 plus u2 y2. And then this particular solution, we can use it after that. This is actually what we have said here. This particular solution is going to be used for the general solution. Okay? And then the general solution of our non-homogeneous equation, as you can see, is going to be y equal, this is the general solution now, it contains all possible solution, equals to c1y1 plus c2y2 plus yp. Okay? Straightforward and easy, and I think that this is the most important equation for us for today. Okay? This is the most important equation for us for today. This is the general solution. Okay? As I said, part of it related to the associated homogeneous equation, and the last part is related to the non-homogeneous equation. Okay, now let's have an example to make everything clear for us, Okay, find the general solution. We're talking about general solution for the following. Y double prime plus 4y equal to sec x. Okay, for the interval, we are talking about some interval from minus pi over 4 to pi over 4. This is our interval. Okay, first of all, how we can deal with this, we are going to look to the left-hand side, which is we call the left-hand side as the associated homogeneous equation. Okay, this is the associated homogeneous equation, which is the left-hand side, and we are going to equate it with 0, right? This is the first thing. If you look to this and go back to the previous video, you're going to find how to obtain the solution for this associated homogeneous equation. Okay? You're going to find that it is constant coefficients here, and we can obtain what we call it the characteristic equation of this associated homogeneous equation, it is going to be like this. Lambda squared plus 4 equal to 0. Do you remember this? Here we have y double prime, it is 1. Y prime, it is not existent, means that is 0. And 4y. This means that we are going to have lambda squared here plus 0 lambda, because we do not have any y prime here, and plus 4, which is the free term, equal to 0. This is our characteristic equation. We can solve it, and we are going to end up with the solution of this. You tell me which kind of roots that we have here. Real distinct roots, or repeated roots, or complex roots, okay? I want you to think about this. Okay, I think that it is a complex root, but anyway, you need to do it by yourself. It's a good exercise for you to recall what you have learned last or the previous videos. Okay, you are going to make it, and you are going to find that y1 equal to cosine 2x, y2 going to be sine 2x. Actually, this is, as I said, the fundamental set of solutions. As I said, you are going to find that your general solution is going to be as if, remember this well, if I call it, it is going to be like C1 e to alpha x, so e to alpha x, and then you are going to say that it is cosine beta, right, x, sorry I cannot write well here, plus another term which is related to C2 e to alpha x sine beta x, okay? So actually this one is considered to be a set of, or one solution, and this one is going to be another solution. You can recall this from the previous videos, as I said. So here we said that e to alpha x, you're going to find alpha is going to be 0, so e to 0, it is going to be 1, and C1 here is going to be used at the end of the final general solution equation. So this means that you are going to find one set of solution, which is y1 of the associated homogeneous equation. This is going to be cosine beta x. Beta here is going to be 2. As I said, this characteristic equation is going, its roots are complex, and you are going to find that beta equal to 2 and alpha is going to be 0. Okay, so you have like C1, or you are going to find that the first solution is going to be y1 equal to as if C1 cosine 2x, and the second solution is going to be y2 like C2 sine 2x. Where is C1 and C2? They are going to be added at the end. They are going to be added at the end. Okay, we are going to find it at the end. In the general solution, we are going to put C1 and C2, but here just use them as if there is 1 is added here. And I put it here as a note, the fundamental sets of the solution, we use them because they are two different solutions. C1 and C2 will appear in the final general solution, as you are going to see shortly. Now look for a particular solution. Now we have finished this part, which is related to exactly the associated homogeneous equation. Now let's go to the particular solution, okay, which is related to the non-homogeneous equation. First, compute the Reniskian. We are going to compute the Reniskian based on what we have obtained here. We have here cosine 2x, which is y1, and its derivative, which is minus 2 sine 2x. And we have here sine 2x, which is y2, and its derivative, which is going to be 2 cosine 2x. The Reniskian is going to be, we're going to use it by the multiplication and subtraction of the diagonals. We are going to end up with 2 cosine squared x plus sine squared x. This going to be 1, as you know, okay? This is going to be 1. Cosine squared alpha plus, or cosine squared x plus sine squared x, it is 1, okay? So this means that our Reniskian is what? The value of the Reniskian is going to be 2, okay? Then the equation 2.11, this is the equation of the non-homogeneous equation. Actually, we can use it, okay? Which is with f of x equal to sec x, which is this one, the right hand side here, sec x, which is going to be our fx. This is f of x, which is the right hand side of the non-homogeneous equation. Okay? Okay. Now we are going to go and get u1. Remember that u1 equal to exactly the integration of y2. Remember that because it's a kind of a silly mistake in exams. Whenever that we are calculating u1, we are putting y2. So y2 f of x over the Wronskian. So y2, and remember the minus here. Sine 2 of x, which is y2, as you can see here, times sec x, which is f of x, over 2 dx. Then we are going to make our integration. The integration of sine 2x, it is double angle. It's double angle, so we can make or use double angle identities, trigonometric transformation. So instead of using sine 2x, we're going to use exactly, it is going to be sine this is sine 2x, like sine 2 alpha, for example. It equals different, we can represent it using different ways. Okay, one of them is, as you can see here, cosine squared alpha minus sine squared alpha. Sorry, this is for the sine. I think that it should not be like this. Is I put only here cosine, but for sorry, yes, this is sine 2x. No, I'm sorry. I didn't put it rightly here. So sine 2x, it means that we are going to use this sine 2x going to be 2 sine x cosine x sec x. Okay, so sorry for this. This would be sine 2x double angle. It is going to be 2 sine cosine. Sine 2x equal 2 sine cosine. And this is sec x here. Then sec x means that 1 over x. So it is going to be 2 is going to be cancelled with 2, and this sec x going to, in the denominator, is going to be cosine, and this cosine cancels this, and then we're going to end up with sine x here, and there's a minus outside, so sine x, and the integration we are going to end up with cosine x. Okay? Okay, this is the first part for obtaining u1. So u1 equal to cosine x. Okay, now let's go to u2. Remember u2, it is related to y1 and then f of x and the Wronskian. y1, it is cosine 2x. Cosine 2x times sine x. Here this cosine 2x is going to be, as I put it before, which is, it is going to be the 2 cosine squared x minus 1. Okay, this is what we call it, okay, the double angle identities trigonometric transformation. Okay, so this is what we have done it here. And then this sec x, it means that cosine x in the denominator, and we have the 2 here, 2. Okay, sorry, this is the 2 as it is. And then we're going to say that cosine squared over cosine, and 2 over 2, they are going to be cancelled, and we are going to have cosine x in this term. And here we have 1 over 2, which is the same here, and 1 over x, it means that sec x. Then we are going to make the integration of cosine minus sec. Cosine, the integration is going to be sine x, straightforward, and sec x, it is going to be the ln of sec x plus tan x. This is from first year calculus, you can get it easily. It is the natural logarithm, is defined only for positive values of x. This is why we put it the absolute sign here, okay, because the logarithm should always be defined for positive value of x. So okay, so now we obtained u2. This is u2 now. This is u2. Okay, so we have u1 and u2. Now this gives the particular solution now. yp equals to u1 y1 plus u2 y2. Right? So u1, it is cosine x. From the previous slide, we have u1 cosine x times y1, which is cosine 2x. Let's go back. Yes, this is u2, and this is y1 and y2, and this value, it is for u1. So now let's go here. Exactly. So we have this u1, and we have y2, which is cosine 2x, and we have here u2, which is already this long, the two terms here, they are, we put them here, times sine 2x, which is y2. The general solution of y double prime plus 4y prime equal to sec x, which is the non-homogeneous equation that we're talking about, is going to be c1 cosine 2x. What is cosine 2x? Exactly, it is y1. And now you can see c1 here, okay? Before we said that c1 was not there, we put it only 1, but now it appears here now. And plus c2, again, this is c2 here, so already we didn't neglect them, just we put them in a later stage, okay? So we put here c2, and then this is y2, and then all of this, as you can see, it is y particular. All of this equation, as you can see, all of this is going to be added here. It is the particular solution. So this is considered to be the general solution, means that general solution of the non-homogeneous equation. The general solution of the non-homogeneous equation. Okay, so I hope by this we have, now this is as simple as that. I mean that the non-homogeneous equation is really easy if you could obtain the set of solution of the associated homogeneous equation. If you could do this, then you are going to find it very easy and smooth, because the particular solution, if we're going back here, we're going to find that the particular solution is pretty easy if you could obtain u1 and u2. It's straightforward. Just you are going to use u1 times y1, u2 times y2. Then you need only u1 and u2. And they are going to be obtained easily, knowing the Reniskian, knowing the f of x, right-hand side of the non-homogeneous equation, and one of the set of solution of the associated homogeneous equation. That's it. So you are going to find it straightforward for you. Okay. I hope that you understand it well, and through this example, I hope that you can stop the video, work the example again by yourself without looking, and try to go through each step of the example. Now let's go to the next part, which is related to the in-class assignment, and this is an important issue. As I said always, whenever we say in-class assignment, then you are going to look to what are the problems that you're going to solve, and then stop the video and try to solve them by yourself first. After that, check the results from the next slides. Okay, so now this is what you should do. We have in each problems 1 and 2, find the general solution using, now we are talking about general solution, okay, using the method of variation of parameters for a particular solution. So we have two examples or two problems, 1 and 2. Take care that here in the first problem, f of x is tan x. Here in the second problem, f of x is going to be, here this is f of x, and here this is f of x, right, as you know. So now, and then you have y double prime plus y, okay, this is going to consist for your homogeneous equation, equating it to 0, and this is y double prime minus 4y prime plus 3y equal to 0 in order to get the associated homogeneous equation and solve it. Okay, now stop the video and work out these two examples by yourself. Okay, stop the video and work out these examples by yourself. Okay. Okay, so now let's solve these examples together. Okay, let's solve these examples together. So here, this is the problem. The first problem, it was y double prime plus y equal to tan x. Okay, so first of all, you are going to separate, taking this part, which is the left-hand side, and equate it to 0. Right, it is like this. We call this the associated homogeneous equation. You are going to find two independent solutions. Okay, so you are going to find y1 and y2. You're going to find y1 and y2. Okay, y1 is going to be cosine x. I hope that your answer was like this. And y2 is going to be sine x. As I said, the fundamental solutions, they are going to be the fundamental set. We call it the take care of this, the fundamental set of solutions for the associated homogeneous differential equation. Okay, because in your solution, you are going to find that this equation is going to have complex roots with alpha equal to 0 and beta equal to 1. So I hope that you have done something similar to this, and beta equal to 1. And you are going to find that your solution is going to be similar to this. But as I said, you're going to find C1 here, and you are going to find C2 here. But as we said, it's not a big deal. We are going to add them at the end. Okay, you can assume them as 1 here, and then we're going to put them at the end for the general solution. Okay, so now we are going to the next step. After obtaining the two independent linear independent solution of the associated homogeneous equation, we are going to the next step, which is the Reniskian. Okay, so we're going to put cosine x, which is the first solution, y1, which is cosine x, and its derivative, which is minus sine x. And here we are going to put sine x and its derivative, which is cosine x. By getting the determinant, you are going to find it 1. I hope that you have obtained this right answer. Okay, after that, to use the variation of parameters, we need to seek exactly particular solution of the differential equation in the form. This is our particular solution, u1 y1 plus u2 y2. So we are going to find that f of x for us, it is tan x. Then u1 of x is going to be minus the integration of y2 times f of x over the Reniskian. So we have f of x to be tan x, and we have y2, it is going to be sine x. So if you tan, it means that sine over cosine. So we're going to end up with sine squared over cosine dx. And then sine squared, it means that 1 minus cosine squared x, okay? Trigonometric transformation over cosine x. Then the integration going to be, this is 1 over cosine multiplied by minus, 1 over cosine multiplied by minus means that sec x, and the minus here. And cosine squared over cosine, it is going to be cosine, so it is cosine here. Take care, minus by minus times minus, it is going to be positive here, okay? So this is a sound mathematical flow. Then the integration of cosine x is going to be sine x, and the integration of sec x, it is going to be ln sec x plus tan x, okay? So this is, okay, this is the case for, or this is considered to be u1, which is going to be the first part for obtaining the particular solution. Okay, now let's go to the second part, which is related to u2, Similar, u2 equals to y1 times f of x over the Reniskian, which is, we obtained it before, okay, and we said that it is going to be 1. And the integration is going to be cosine x times tan x. This is f of x, and this is y1 of x. This means that cosine times tan, it is sine over cosine for the tan. Then we are going to end up with sine x, the integration of sine x, right? And then we are going to end up with minus cosine x. Now we know u1, and before here we know u2. This is u1, and we know u2 now. Minus cosine x, and here it was this one, u1 equals to this one, which is sine x minus ln sec x plus tan x. Okay, now the general solution can be written as, this is the general solution, which contains all the solution of the non-homogeneous equation. C1 cosine x plus C2 sine x. Now here, this is one of the fundamental set of the associated homogeneous equation. Okay, we call it, this is as if y1, and here it comes the constant. As we have explained before, it will appear at the end. Okay, so we didn't neglect it, but just we put it at the end. And here sine x, which is, this is y2, and we put the constant here, plus y particular. Starting from here, ending with this one, it is going to be y particular. What is y particular? It is going to be sine x cosine x. Okay, what is sine x and cosine x? Yes, we have u1. Let's go back. Yes, this one. u1, y1. Here, this is u1, y1. Back here, this is u1 times y1. u1, as we said, it is going to be this value. Sorry. So this is C1, I think. Yes, that's right. So we have like C1 cosine. This is C1 y1, C2 y2. So we have y1 here, and we have y2 here. Okay. Then after that, we are going to have the particular solution. The particular solution means that we are going to use u1 y1 plus u2 y2. Here we can distinguish that this one, ln this one here, it is the sine x cosine x minus cosine x ln sec x plus tan x. This is related to u1 minus sine x cosine x, which is related to y2. So we have y2, which is sine x, okay, and we have cosine x, which is related to u2, minus cosine x, which is related to u2. So anyway, you are going to find that from here to here it is y particular, and we are going to rearrange them because we have a lot of cosine and sine that is considered to be common factors. So we're going to put c1 cosine x, c2 sine x, and then we are going to end up with the y particular to be cosine x ln sec x plus tan x. Take care that we have this ln sec x tan x, and we have sine cosine here, and we have cosine here, and we have sine cosine here. Okay, so this one I think cancels this, and then we are going to end up with minus cosine x ln sec x plus tan x, which is already here. Okay, I hope that you ended up with the same solution, okay, for the general solution of the non-homogeneous equation. Okay, now let's go to the second equation, or the second problem, which is this problem. Let's go and solve it here. So this is our problem here. The right hand side is going to be f of x. This is the right hand side, and the left hand side is going to be the y double prime minus 4y prime plus 3y. Then we are going to end up with, or we are going to do the same procedure. This one is going to be considered as associated homogeneous equation, and we are going to find y1 and y2 for it. Okay, so y1 is going to be e to 3x, and y2 is going to be e to x. Seemingly, I hope that you found this when you solved it by yourself. It seems that we are having real distinct roots for this associated homogeneous equation, and the characteristic equation would have the roots of lambda 1, okay, equal to 1, and lambda 2 is going to equal to 3. Okay, so this is the solution of the associated homogeneous equation. I hope that you have solved it as we said. Okay, so y1 e to 3x and y2 e to x. And we are going to have the Reniskian. The Reniskian easy for you to obtain it because we have exponential functions, so you can arrange it as we have explained before. We're going to find that it equals to minus 2 e to 4x. Then we're going to the same procedure. u1 and then we're going to obtain u2 after that. Here, u2, I think this is a kind of a small mistake. This is supposedly to be u2. So we have here u1, okay? So u1 is going to be the minus integration of 2 e to x cosine x plus 3 over minus 2 e to 4x dx. And then we're going to integrate, because as we said, this is y1 times f of x over the Reniskian, which is already we have obtained here. The integration is going to be like this, e to minus 3x cosine x plus 3. This is e to 4x and this is e to x. Then we're going to end up with e to minus 3x times cosine x plus 3. Then you can make this integration. It is from the first class calculus. You can obtain this integration and end up with this. I hope, as I said, you have done it well. For u2, I think this is supposedly to be u2. Okay, so the integration is going to be y1, which is e to 3x, times f of x, which is 2 times cosine x plus 3 over the Reniskian that we have done. Rearrangement of this, it is going to be e to minus x, because we have 3x here and 4x here, so it is minus x here, cosine x plus 3, and 2 would cancel with the 2 here. Then we have this integration. You can integrate it easily, and you can find that integration by parts would yield this value. Check it and let me know if there is something wrong in this. Then the general solution after obtaining u1 and u2, general solution is going to be c1 y1 plus c2 y2. We have y1 here, and u2, which is here. I think this is u2 here, and u1 here, this long one. It is a very long terms here, or the many terms here, but anyway, it is easy at the end. So we're going to find that here this is c1 y1 c2 y2, and then we're going to end up with this particular solution, all of this. Okay, so take care that, because u1 y1, it is going to end up because u1 y1, as you can see here, it is e to 3x, so it is going to be multiplied by, we have 3x here, minus 3x here, and minus 3x, so they are going to be like vanish. So the exponential term would vanish, and only we are going to the only remaining is going to be the number or the fraction and the trigonometric or the sinusoidal functions, cosine x plus 3 and sine x plus 3. Similar here, we have e to minus x, and we are going to multiply by y2, which is e to x. So you are going to find the exponential function is not appearing here, vanished already. We are going to left with cosine and sine, and with the fraction half and half here. Then we can rewrite this rearrangement of this term. Then we're going to end up c1 e to 3x, c2 e to x, and then after rearrangement of this 4 terms, we can end up with 2 simple terms having 1 over 5 cosine x plus 3 minus 2 over 5 sine x plus 3. Okay, this is the final solution. I hope that you have obtained this final solution when you solved it by yourself. Okay, now this is the end of this video. I'm going to show only the home assignment that you should do. Okay, and after that I'm going to wrap up the video. So this is the home assignment. This is the home assignment. Y double prime plus 9y equal to 12 sec 3x. Find the general solution using the method of variation of parameters for a particular solution, as we have done before. Okay, so now I'm going to recap and give a short summary of what I have explained for today. Remember that our today's lecture or video, it is related to the variation of parameter. What is the meaning of it? It is only a way for the solution of the non-homogeneous equation. Okay, so what we have done here, simply we said that if we have a non-homogeneous equation and we want to solve it, we need to solve the associated homogeneous equation first, which means the left-hand side, we're going to equate it with 0 and solve it as we have explained before using the constant coefficient method, as we have explained in the previous lectures. And after that, after having y1 and y2, we are going to put it as part of the non-homogeneous general solution of the non-homogeneous equation. And the remaining part is going to be the particular solution of the non-homogeneous, which is going to be explained, or we are going to obtain it by using some method. This method, we call it the variation of parameters. So we are going to obtain, we already explained about these strategies. The point is we are going to find, we are going to find y particular by, or relying on something called u1 and u2 multiplied by y1 and y2 respectively. But what is u1 and u2? We found that they are going to be related to y2 of the homogeneous or associated homogeneous equation, and u2, it is going similarly to be related to the y1 of the associated homogeneous equation, the first solution of it, and then the right-hand side of the non-homogeneous equation and the Reniskian, which is already we have explained before, and we know how to obtain it. Using u1 and u2, we can obtain y particular easily, and then we can end up with the general solution of our non-homogeneous equation, which is going to be c1 y1 plus c2 y2 plus y particular. And then we have a couple of examples for this. I hope by this video you have an idea of how to solve the non-homogeneous equation and how to go through the variation of parameters method in order to obtain y particular and then the non-homogeneous general solution. Thank you, and see you in the next video.